I'm happy to introduce my colleague, Dr. Satya from IIT Goa. So Satyanath did his PhD and MSc in engineering from IISc Bangalore. And after that, he was a postdoc researcher at NUS Singapore. He has also worked as an intern at Xerox Research Center in Grenoble, France. And before that, before joining IISc, Satya was a software developer for 6 years. His research interest is in the area of machine learning and game theory. So looking forward to your talk, Satya. And also I'm looking forward to interacting with all of you at the end of this talk. Think of it like a tea session. Sorry, this is an online talk, but think of it like a get together and a tea session where we will discuss ACM activities and so on. So thanks, and over to you, Satya.
Thank you, Neha. Thanks, everybody. So during the course of the presentation, if my voice is not audible or any other problem that you may face, please bring it to my attention because I may just go on a monologue. So you must interrupt me in case there is some issues, right? So yeah, so let me just, so this is going to be a whiteboard talk. So I will present my writing window, and then we will just walk through the agenda of the talk. Okay, so before anyway commencing, I must thank all the ACM members for having invited me, in particular Professor Kamath for giving me the opportunity to speak to all of you. I think it is very nice when we have a collection of so many different experts from various fields, and it's nice to always present to a very very smart audience, right? So welcome from my side for this talk. Okay, so let me get started. So we will begin by a very quick overview of what are the mathematical. So the purpose of this talk is to basically be a motivation for why one must study things like probability, statistics, and things like that. So towards the aim of trying to pick up areas such as machine learning or AI, right? So if you really look at this field of ML/AI, right? So if you look at what is the kind of prerequisites that one must have to learn this, you will find that there are 3 different types of pillars that this entire subject relies on. The first one being probability and statistics. The second being linear algebra. And the third one, which is optimization. And that actually is in turn driven by ideas from calculus. Okay, so it's a very mathematically inclined field, but sometimes, you know, we have so many nice packages, so many nice libraries that we just use them without really understanding why some things have been designed in that particular way. I mean, this is common, right? I mean, if you are using, let's say, a AAA battery, right? The small, the cell, you know, the pocket cell, so to speak. So we don't know what's inside those, right? So having a black box idea of ML/AI is okay, but sometimes, as long as things are working, it's fine. But sometimes things don't work, and that is when you need to debug your models, right? So you start. You try with some algorithm, it doesn't work, and then you don't know what to do. So you will try some other algorithm. So what I'm trying to say is like a better approach. This can be developed over the course of your studies or your time, right, that you are devoting for ML and AI. You can start to look at these underlying mathematical ideas that drive this field. Okay, so today we will just be focusing mainly on probability and statistics, and we will try to see how ML/AI uses probability and statistics in general. Okay, so yeah, so I mean, as I said in the beginning, so you always please feel free to interrupt me, and we will not try to have a separate question and answer session towards the end, at least for the talk. So you can always interrupt if some things are not making sense, right? So let's delve right into the subject, and let's try to see what does what are the important elements of ML and AI which are directly coming from probability and statistics. Okay, so if you have done a course, or if you are sufficiently well versed with ML, you will know that there are three types of, roughly, there are three broad categories of learning that we have. One is supervised learning, right? So here we have classification, and then we have regression. Okay, so these are the two broad supervised learning algorithms. And what is a classification? So this is like you are given some set of features or some evidence, right? So you are given some set of x's. So for instance, if you want to predict a particular person has COVID or not, right? So no talk in this times is complete without mentioning this COVID-19. So suppose you are given for a patient several features, right? So amongst the features, it's like high fever. That is one feature. So if it is this particular feature x1 is set to 1 if the person has fever, 0 if no fever, right? So then you have x2, which is 1 if there is loss of smell, right? So you may have all these kinds of features that are given to you. Okay, so this third one could be like, I don't know, maybe a taste, loss of taste, all these things. So these together will form the features. And what is the thing that you would like to output? So why I, for the given xi, what we would like to produce, tell, this is the prediction that I would like to do, is one, if you want to predict if COVID, right? You want to predict 1 if it is actually COVID, 0 otherwise, right? So this is a simple classification task, right? So now likewise we can look at regression task as well. So in regression, what is happening? So you are, instead of trying to predict 1 or 0, you may be trying to predict something else. So what you would like to predict, for example, could be like house prices. So yi is the house price. Okay, so house price, let's say in Mapsa, right? And then what are the features that are given to you? So you are given features like number of bedrooms, then land area, and pin code maybe. And you would like to produce output. I mean to say, you would like to output what is the house price. Okay, so this is like very standard classification and regression problems. If you haven't seen what it was, now you know. And how does probability come in here? So actually the foundation of this classification and regression problem already was there in probability. So the classification in particular is actually saying, so what is the probability that yi is 1, which means the person has COVID, given that he has these features, right? x1, x2, all the way till xn. So that is what is a classification task. So this is a classification task. Okay, so what I'm trying to say is that classification is essentially conditional probability. Okay, and the theory of Bayesian decisions, it actually shows that this is the best you can do. There will be no classifier better than Bayes classifier. So this is a result. Let me just state it without proof. So let me say in a positive way. So Bayes classifier is optimal. Okay, so what is a Bayes classifier doing? So it is going to compute the conditional probability of y given the set of inputs that are given to you. So I will briefly tell you what is a conditional probability and how to think of it via a example. But I just want to show you that all the things that we see in a machine learning algorithm has a probability counterpart. Okay, and so this is for classification. Similarly, for regression, the optimal regression output that you should get if you are doing well is you need to be able to compute expected value of yi conditional on all the features that are given to you. Okay, so x1, x2, all the way till xn. So in the house price example, what you would like to say is you would like to compute this conditional expectation. Okay. So as you can see, these two broad things are directly concepts of probability. Okay, I will just explain a little more on what is conditional probability, what is conditional expectation little later. But I just want you to, walk through with me on the entire space that we have, right, in this machine learning. So this is about supervised learning. So let's look at some unsupervised learning algorithms, right? So the second category is unsupervised learning. So here, what is meant by unsupervised? So what you are given is data. Okay, you are just given data. You don't know anything else about it. So using the data, you would like to arrive at some patterns. So what is an example for this? So let us say you are in the Indian government tax. You want to find out if there are some fraudulent transactions going on, right? So how do you do that? You cannot check every person's account and every transaction being made, even though you may have the permission to do it because you are the government and it is your duty to supervise and monitor what's happening in the country, right? So you can actually go and see everybody's account. So that's permitted, right? But you cannot do it because manually you may not even be able to detect, right? So what is it that you could do? So what one can do is like you look at the existing data that you have and then come up with some kind of a pattern that explains the data, and every new transaction that is done, you check whether it is anomalous or not. So this is called as anomaly detection. Okay. So anyway, I haven't told you very clearly what this is. So let me give a much simpler example. So what we have here, there is a very famous data set, which is called as, I don't remember. Okay. It is called as, like you are looking at this geysers, right? I don't know if you pronounce this as geyser, but geyser or geyser, whatever this is. So this is like underwater hot water. This it from time to time there is a fountain like a jet of underwater this water shooting out from the ground. Okay, so this happens periodically because of volcanic activity. So under the surface there is a huge water body, right? And it mixes with another source of lava. Okay, and when they mix, it produces hot water and steam, and that erupts from the ground from time to time. Okay, so this is called as a geyser, and this is an example. So I'm trying to give you an example of what is anomaly, right? So just to give you some background on what is an anomaly. So what you have is that this is happening in the world. I mean, this data has been collected from some spring in US, and what they do is they plot two things. Okay, so they plot waiting time. So what is waiting time? So between two geysers, two eruptions, what is the time? Okay, so this is time in seconds. And then they look at eruption time. So let me write it this way. Okay, so if at all the eruption has taken a lot of time, okay, so then what it probably means is that it has the water and this thing have been mixing, but they have not been able to come out, right? So what happens is when the eruption time is when the waiting time is large, then the eruption time also tends to be large. So if you plot all these data points, you will have something like this. Okay, and similarly, if the waiting time has been short, so that means just now there was an eruption and immediately there is one more eruption. So then typically what happens is that you will have some pattern like this. Okay. So now what you can do is you can run a popular algorithm which is called as k-means. Okay, I will not explain what k-means does, but it is actually doing one thing only. So what it is trying to do, it is looking at the data and it is looking at the probability that you see a particular data, and it tries to find best explanation argmax of that data. So this is like theta k-means. Okay, so what it tries to do is it tries to find out, for looking at the data, what is the best underlying explanation for the data. Okay, and it learns that. And if there is an anomaly, how does the anomaly can happen? So anomaly can happen in two ways, right? So what can happen is the waiting time has been very short, but the eruption time is long. So this could be one anomaly. Or the waiting time has been long and the eruption time has been not so long, right? So something like this. So these two are like somewhat anomalous. So this should not happen frequently. Okay. And suppose if this keeps happening now, then what can one conclude? Yes. So maybe you can conclude that the volcano is becoming more and more active, right? So that is what you can conclude. And if this is happening, then you can say that probably the volcanic activity has died down, the lava has cooled, right? So that's why this may be happening. So this is an example, and here again in the example you might have missed it, but let me reiterate. So you are again doing some kind of a probability question. So this is also a probability question. Okay, so this is the second example. So now moving on, are there any questions, comments so far? Okay, so moving on, the third important category that we have is called as reinforcement learning. Okay. So reinforcement learning, where is it used? So this is used very often in self-driving cars. It is used in like if you want to find out the best way to play a particular game, right? And if you want to basically learn from the environment. So there is an environment, you do something and you try to find out the optimal way of doing something. Okay, so this particular topic is actually heavily related to what is called as Markov decision process. Okay, and this also is based on what is called as Markov chains. Okay, and that is also a probability question. Okay, so all the three important pillars of machine learning are based heavily in probability. They are defined in probability. Okay, so in fact, if you try to look at, let's say, some kind of a deep learning algorithm or something, it is essentially indirectly trying to find out what is P of y given x, or it is trying to find out expected value of y given x, conditional probability. So even though we may not feel it that way, underlying thing is that. Okay, so in fact for k-means, right, if you look at the algorithm, it doesn't seem to, you don't realize that it is doing some probability question, but actually what you're trying to find out is this. So you are trying to find out two things. One is argmax. So you are trying to find out the cluster centers, right, the centroids, so to speak, and you are also trying to find out this, like one single parameter which is representing the thing, like how spread out it is, right? So this is the sigma. So it tells you how big these circles are. Okay, and it is trying to find out a normal distribution, sum of two normal distributions that explains this. So normal mu1 sigma I, sigma squared I, plus normal mu2 sigma 2 6. Yeah, so it's trying to find out, so x given this, x is coming from this. So even though you may not realize it, the underlying thing is still a probability question. Okay, so this is what I just wanted to introduce, like how all the popular machine learning algorithms, machine learning techniques that we know are underlying probability questions. Okay, so this
So
was
Satya,
yeah.
So the carrot and stick method that the parents use on their children, is it a reinforcement learning?
Yes, definitely.
Huh?
So
Huh?
yeah, that is because every child has okay. So reinforcement learning in a Markov decision process, let us say, it has two things, states and action. See, this is the beauty of doing a whiteboard talk, because now I can go into this because there was a question, right? So anyway, so there are states and actions. So states, you can imagine for the child being naughty, right? Naughty, very naughty. I think these are the only two things. Okay. And action is like, so action could be like break TV, break vase, right? And then depending upon what actions happen, they get some kind of a reward. Okay. So there is a plus. So the actions will give a reward based on the actions, right? So there is a reward, and based on the reward, the child is trying to learn whether it should continue to do these things like that. So it can change from one state to another. All these things can happen. Okay, so I mean, without going into too many details, yes, it is a kind of mark-out decision process. Yes. All right. So moving on. So I would like to, yeah. So since we have looked at like in the supervised learning setup, right? There are two things that are frequently coming, which is conditional probability and conditional expectation. So I will look at some contemporary examples that we see in day-to-day life, where these kind of questions are being answered. Okay, and we will go through like things that we are seeing in the newspapers today, right? So I have, for example, 2 days ago, this paper appeared. So this was, if you had seen the newspaper article, let me just show you. Can you see this? No, I suppose. Are you seeing my white screen only?
Yes, sir.
Okay. So anyway, so I will show you the article that I'm talking about. So it came, I think yesterday or day before yesterday. So, how does one go about trying to understand something like this, right? Single shot doesn't offer much protection against COVID. So there is a Delhi study, and this is the study. Okay, so if time permitting, we will try to reach here. But along the way, we will look at what is conditional probability, what is conditional expectation, and so on. Okay. So, yeah. So let us look at very common thing. So as you all know, RT-PCR, right? RT-PCR has been made mandatory whenever you travel between one city and another. Okay. So my question is, so we are all, at least scientifically inclined, right? So should we do it or not? I mean, is it a good policy or is it a bad policy? What can happen, right? So this is the underlying question that I'm trying to attempt to answer. Okay, so let us try to systematically see what are all the characteristics that one knows about RT-PCR. Okay, along the way we will understand what is conditional probability and whether something like this can be useful, need not be useful. All these things we will try to see. Okay, so RT-PCR is the gold standard COVID test. Okay, so this is used throughout the world as a gold standard. So what that means is it is belief. There is a belief in the community about this. Okay, so anyway, so there are two parameters of importance for RT-PCR. So one is called as sensitivity, and another one is called as specificity. Okay, so what is sensitivity? So sensitivity says, so probability of getting a positive test outcome. Okay, so this is important to understand this difference. Okay, so what am I saying? So what is the meaning of taking? So if you take the test and it comes out positive, so that is completely different from actually having the disease, right? So what sensitivity is saying is, what is the probability of getting a positive test outcome given that patient has COVID? Okay. So as you can see, this is This is actually a conditional probability. So how does one understand conditional probability? So, so this is the question that I will try to answer. So before that, let me just talk about what is simple probability. And so if I ask what is the probability of a random citizen, so if I pick somebody walking in the street, and what's the probability that person has COVID, right? How does one answer this?
By looking at the past data.
Yeah, so exactly. So you look at the population. So the sure short way of doing this is look at total population, right? Look at total population, and you look at total number of people who have COVID disease. Okay, not the test being positive. They actually have the disease. What means, so how do you ensure somebody has a disease? You do many tests, not just one RT-PCR. You will look at the lungs, you will look at the temperature, that. So if you could do this, this is a good estimate, right? This is the exact estimate, but often enough we don't have that. So what we will do is we will do some kind of sampling. We will not look at the whole population. We will just look at some amount of some 100 people, and then we will look at this. So this will give us a number, right? So this is called as I'm getting a message saying that my internet connection is not stable. So if there are any interruptions, please let me know. Okay. Okay, so this number, if you look at how the disease has been progressing, this number could be something like 1%. So if you look at 100 people, most likely 1% out of that 100 people may have. In the peak, it could be like about 4 people. This number could be 4 people. Okay, so this is your conventional vanilla probability. Okay, so when we say patient has COVID, what we are saying is you are looking at population. So the denominator here will be the total population, okay, with COVID. So what we do is we do several tests, and we find out all the people with COVID. We collect them in a room, and on those people we will administer the RT-PCR. Okay, and we will see how many of them have positive in this population. Okay, so what is this population? This population is the population with COVID. So this is called a sensitivity. So it's important that you understand this. So is this clear? What is the difference between the above and the below? So what is the difference between this and this? Okay, I'm assuming it's clear.
Yeah,
so this,
so it means that there is a chance that somebody in the population may turn out to be negative in your test, right? I mean, there is
who actually has COVID, but still it will show negative. Okay, so this number, I mean, last I checked is 0.67. Okay, so for RT-PCR, so this is that number. And similarly, specificity is probability that the patient tests negative given patient, or let me not say patient, I think I should have said person throughout, but okay, person has no COVID. Okay, so this is called a sensitivity, and for RT-PCR this number is 99. So if I look at all the people who do not have COVID, right? So the formula here, how do you think about it is this: you look at total population healthy, and then you look at negatives in this population. Okay, that means what is this population? The population which is healthy, and you look at it. So what this means is that 1 out of every 100 healthy people will actually test positive, right? So this is negative. So what it also implies is that person will test positive test, but no COVID. This is 0.01%. Okay, so this is the actual statistics of this particular test. Okay, so what was the question that we wanted to do? So we wanted to know whether if we just randomly do RT-PCR tests, if or not it is good or bad. That's what we want to know, right? So that's what the underlying question was done. So, but this is what people do, right? So in China, for example, I mean, at least if you believe the newspaper articles, so whenever there is a wave, they test the entire city, right? So what does it give? What are you going to get if that happens? If these numbers are accurate, okay? So this is what I picked up from newspaper articles. Perhaps it is more or less, I don't know, but this is what I got from that. So now, the question, right? The actual this is called as an inference question. Okay, so the inference question is, what is the probability that the person actually has COVID disease, right? Given he tests positive. So can you understand the difference between this one and this one? So I have basically flipped the two things here, right? So here what we are looking at is, we are looking at people, we are looking at the population, all of them who have tested positive, okay? And then I'm asking, amongst this population of people who have tested positive, so how many actually have the disease? Okay, so this is called as an inference problem. Okay, so now we will try to attempt to answer this. So are there any questions till this point? Okay, so I will use my calculator for this calculation, but I will tell you how it is done. Okay, all right. So what we need to do, if you want to do this, so what we need to do, let us try to understand. So the formula we know, right? So we look at total population with positive test. Okay. See, I'm trying to use intuition. I don't want to use the formulas. I want to use intuition. Okay. So I will do some kind of inaccuracies. I will make small mistakes with purpose so that we all understand the underlying message. Okay. So the actual math formula is very similar. Okay. And that will give you the accurate answer. But here I'm trying to just give you the idea of how it can be done. Okay. So this is positive with population with positive tests. So if you look at this, what is the numerator will be? So positive test. So number of people with positive test, because that's a population, and COVID disease. Okay. So let's assume, so to do this calculation, so let us assume that the population is this, right? So 1 million. So this is the total population. Okay, so let's try to use what we know and try to compute this denominator. So who are all the people who will test positive? So there will be people. So yeah, so to test positive, there will be people who have positive tests and no COVID, right? And there will be people who have positive tests and COVID. So these are the two people, right? Either person has COVID or doesn't have COVID. Okay, so these are the two people. And in the numerator, we will have positive test and COVID. Okay. So let us try to find out how many people actually have COVID, right? So first we will try to do that. So I have told you in the very beginning that the total proportion of people having COVID is like 4 in every 100, correct? This is what we assume, that this is a reasonable estimate. So 4 in every 100 means for a population of 1 million. So 4 for every 100 will mean that there are totally 40,000 people who have COVID. Is that okay? I mean, this is approximate, okay? These are all calculations that I'm doing, which is not correct, but approximately, let us say there are 4,000 people, 40,000 people having COVID. So what did I do? Because I said that 4 in every 100 will have COVID. So there are 1 million. Okay. So that means 4 in every 100 will translate to 40,000 COVID people. Okay. And no COVID obviously will be this number minus this number. So what is that? So somebody should help me here. 960000. Is that okay? I hope it's okay. Yeah. All right. So now coming back to the test, right? So what did we say? Amongst all the people with COVID positive, only 67 in every 100 will actually show positive, right? So positive and COVID, okay, will be, so 67 for every 100. So for 40,000, what does it mean? So these are all 7th standard question, right, of ratios and proportions. So I will just multiply and tell you, but you can check 67 into 400. So this is something like 26,800. Okay. I hope everybody understands, right? So all the COVID people, not all of them will test positive. Only 67 out of every 100 will test positive. So this is the number. So similarly, no COVID and positive, what is that number? So that will be, let's try to do that. 960 into 1 in every 100 will show wrong result. So that number will be, that is easy computation. That will be 9600. Okay, 1 in every 100 will show positive. Is that okay? Does everybody understand these two computations? Okay, so now if you put these numbers back, okay, so you will have 9600 here divided by 40,000. Sorry, what was that number? 26,800. Plus 9600, right? So this number, if we compute, let me see what that gives. Can someone compute this and tell, or maybe I will do it. 9600 plus 26800. So this number is 0.26. Okay, what does this mean? So this means that, so this is the inference that we have done. So if somebody tests positive and if you are looking at no other information, the chances that the person actually has the disease is just 26%. Okay. So unless you look at other features saying that the person actually has fever, doesn't have smell, and all these things, only when you put together all of them, then only we can make conclusive results saying that that person actually has COVID. Random testing will give you this number. Okay. So I hope this is like, I wanted to give you a quick introduction of what is conditional probability. So is this all right? Okay, so I will assume so far things are okay. And this particular formula is what is called as Bayes rule. Okay, so I haven't used the Bayes rule in its formal sense, but it is somewhat similar. Okay. All right, so this is Bayes rule. So this, I mean, you can, even though this is a conditional probability question, this idea has been existing all throughout in the history of, I mean, as far as we can go, even 200, 300 back years itself, people had this idea, Bayes rule, right? So if you want to find for various things, this was what was used, right? So even now in the modern context, we use it in machine learning, but this is an old idea. So that's essentially the point I'm trying to make here. Okay, so this was one. So next, I will give you an example of something that was done in 1940s. Okay, so this is an example of a regression type of thing, which was done in 1940s. So the question that people were trying to answer that time was, you want to find out what is the production of jute, okay, jute bales. Okay, so I have some data that I have noted down from some other source, but the question is, you need to predict how much jute is going to be produced in some 1940s, one of these years. Somebody wanted to find out in the state of Bihar, I think, right? So jute is a fiber that is used to make bags, and it was very popular earlier, but I don't know whether it is so popular now. But it's a material that is used to make packaging. Okay, so it's a cash crop, right? So cash crop. Okay, so it's even now in modern context also, there are many startups which are trying to predict what will be the production of wheat, cotton, all these various types of things they would like to do, right? So there are advantages of being able to do this prediction, because then you can take care of how do you want to distribute it, and how do you get good prices for the farmers, and in the next year what you need to invest. All these things are done as a chain. Next stage is that. Okay, so this is a cash crop. So what used to be done by the government at that time is that they used to have something like 33,000 employees. Okay, so this was the government method. Okay, so 33,000 employees used to go to the farms in Bihar, every district, every village. They used to go, they used to talk to the farmers, they used to try and estimate what is the production. I mean, what is the jute? What do you think will be? And they will try to collect the data, and then they will try to predict it. So this is like, you have to talk and you have to find out what is going to happen and then try to collect it. Okay. The aggregate cost of this exercise in 1942, based on the source that I have, was 82 lakhs. Okay. So this is a big amount in 1940s. And the value that these people came up with in that one of those years was 6304 into 400 pounds. Okay, so this was the estimate given by the government method. Okay, and at the same time, there was a very popular statistician. His name was PC Mahalanobis. Okay. Okay. I'm not that good with spelling, but I hope this is correct. So this person also had another method which was called a sample survey. Okay. So the sample survey method, what it does is you randomly pick, you randomly pick a subset of individuals in this. Instead of trying to go for every village, every district, every field and talk to people, you'll just do a random sample, and then using the random sample, you will try to extrapolate. Okay. So this is like your regression problem, right? You are trying to predict this Y, right? Y is your output variable that you would like to predict, right? And what was the investment required? They had 700 trained sample gatherers, and the cost was 8 lakhs. And the prediction they made was 7540 into 400 pounds. Okay. So this was there was two different outputs. And then when the actual, after the year was over, and when people looked at the actual production, the actual production in that particular year was 7562. Okay. So you can see that like a statistics based method sometimes will be very good. Okay. And yeah, so this idea I'm going to talk a little bit more, but I'm just trying to motivate that this is, so now in the modern context, so what did they try to do? So when Mahalanobis tried to do this, so it was expected value of X, Y, which is your, how much jute do you want to predict, given your sample survey, right? So given village 1 said this, village 2 said this, all the way till village some 700. I don't know how much was collected, but whatever they said, you came up with a value and that's what you predicted, right? So this is what in the 1940s it had happened. In the modern context, what we will do, we will look at expected value of y given satellite image 1, you will look at given IoT output 2, right? And then given expert input 3, given sample 4, all these things will be part of some modern context things, right? So your features will not be directly going and visiting villages, but it could be from various handheld devices, right? And if you can do this well, I think it addresses very important social problems that we have, right? So essentially the problems have been solved quite early itself. Okay, so that's the whole thing that I'm trying to say. All right, so this is just another example, and let's look at a few more examples before we move on. Okay, you please feel free to interrupt if there are any questions. Right. Okay. So now the third thing I would like to talk about. See, the whole agenda of the talk was to basically show you what are the theoretical underpinnings of machine learning AI that I have shown you already, and then to walk you through several modern applications where it is being used, right? And which is also.
So Satya, I have a question. Okay.
Yeah.
So sampling is very important, right? I mean, the way you sample, right?
Yes.
But how do you know? See, ultimately, my prediction when it is going wrong, I know that maybe my sampling was not good. You know, like the way they do during the election, right? I mean, somebody predicted, somebody is very good in predicting, whereas somebody is not able to, right? But that is after I know the ground truth, what has happened, right? But at the time of sampling, do I know whether I'm collecting good sample or not?
Yes. So, Professor Kamath, I mean, since you asked this question, and I was actually going to opinion poll next, but I will ask you one question. So let's say that there's a pin like this, right? So there is a pin, and I'm dropping a hard ball bearing, right? A metal ball, right? If I'm dropping it here, it will bounce off this either to this direction or this direction, right? Correct. So can we reasonably predict this? I mean, just rhetorically, but of course you can say, but can we reasonably predict this? It can go either way.
Provided I know the entire geometry and the physics that goes behind it.
Yes.
Right.
Very good. So if we know the geometry and physics, that is always better. So if you, let me just say, since you bring that up, for any machine learning problem, if you can use the physics and the domain knowledge, if you can use that, that is the best thing. Nothing like it. But what we are trying to do in machine learning is we are trying to study the uncertainty. So we can only talk about probabilistically and not knowing too much information. We just look at the data, right? So if this experiment, for example, was repeated like many times, so roughly 50% of the times it will be on the left, 50% of the time it will be on the right. This should be obvious, right? I mean, there is nothing we can do in this stage, right? So, but if we repeat this in a particular setup, which is called as the Galton board, which I will show you now. Control Shift print screen. You might have seen this in science, like planetariums and things like that. Oops, not this. Yeah, so Professor Kamath, now if you see, when you arrange it like this, it always comes like this, like a Gaussian. So what I'm trying to say is that even though you don't know anything beforehand where it will go, see, there is nothing preventing it from falling here. But what happens is, in order to reach on this basket, once the ball hits here, it has to hit here, it has to hit here. You know, it has to continuously take this completely difficult path, and then it has to fall here, right?
So here the small balls are thrown from the top, and they randomly bounce against this small
Yes,
pinholes,
yes,
and then they
yes.
fall, and this is the pattern that you get at the below. I
Always.
see.
That is the point.
I see. I
Always.
see.
Okay. So now, what is the analogy for this, and what is the analogy for opinion poll? So your opinion poll. So there is a true pattern that is there. So this is, let us say, the true pattern, but your opinion poll is like few balls that we are putting, right? So you have to be particularly unlucky to get a very, if you are truly done a random thing. So instead of having these many balls, if I just did let's say a subset of the ball, so this is like your actual election happening. But if I do random sampling, and if I try to estimate, then I will get not fully like this, I'm only doing a sample, right? I will get a small pattern like this, right? uh, Professor Kamath, do you understand what I'm trying to say here?
Yeah.
Because yeah, because even though I may not have all the so if that's why we have to repeat many times before we can say reliably. So whenever you are doing an opinion poll, it has to be repeated. You have to ask many individuals, and it has to be truly random. So you cannot, for example, go to an airport and ask people only at the airport, right?
Correct.
Because people at the airport are coming from some background, so that will not be a good representation. So you cannot ask in one colony, you cannot ask in one village, one panchayat, one state. You have to go everywhere, and you have to ask people without looking at anything else but your list that you have. That is the way to get reliable estimates. And if you do that, this is what will happen, right? This is what will happen, because it's just bound to happen. And the reason is, again, this, you know, when you are doing truly randomly, getting an overestimate, underestimate, both are likely. In fact, getting somewhere near the actual estimate is more likely. And this is what is called a central limit theorem. So this is like one of the underpinnings of statistics, which is called a central limit theorem. Okay. So what actually it does? So now opinion poll is one example where you want to predict the election outcome before the election is actually held, and you ask randomly people, and then you try to find out whether they support a particular person or not, and then you look at the proportion. So proportion of people supporting a party A is total samples. Okay, total samples. And here in the numerator, people in sample supporting A, right? So this is what is we do. I mean, I'm just writing some very silly thing, but this is the proportion of in your sample. This is what it is. And the true underlying thing is PA. So your sample, which is I'm showing with a small hat, you would like it to be close to PA hat. Okay. So now what statistics gives is a confidence interval. So that is the next thing that I wanted to tell. So it gives you a confidence interval. So it tells you that with 95% probability, or whatever probability that you want, if you have done enough number of samples, it will tell you a range. Okay. It will say the support people who are supporting this party is maybe 52 to 56, like that they will say. Okay. And
There is a question
that
in
number
the
is
chat.
reliable. Sorry.
There is a question in the chat window.
Okay. I will see. Perhaps can you I don't I am little bit not used to this setup, so can you ask what was the question?
So there is a question from Vaibhav Sinai Pisurlikar. He asks, what would be a good sample size, and is there a criteria on which we can decide that a particular sample is too large?
Hmm. Okay, so there is a very concrete formula. So given okay, so here, right? So this I'm just giving an example here, but using central limit theorem, okay, you can get exact formula. So like exact formula for what is the interval. So as you increase the sample size, this interval will shrink. Okay, so there is an exact formula to do that. So just that it is beyond this particular scope of this talk, but I will show you one example if I can share that. Mm, okay, I have written a code, maybe. Yeah. So can you see this?
Yeah, it's visible.
Yeah. So so this is like a code that I wanted to show. So here, assume that there is a underlying true ground truth that we don't know, right? So this is like what Professor Kamath was asking. This is like after the election happens, I will find out that 67% of people actually supported one party. So this is the ground truth that we don't know. And let us say we do the samples, right? So if I ask, for example, here, if I ask 100 people, you will get so many, depending upon when you ask, you will get a curve like this, okay, for 100 people. And if you repeat this with 500 people, it will look something like this. Yeah. So what is the thing that's happening? If you notice here, the variation is much larger here. So it is 0.50 to 0.80, whereas if you ask 500 people, it is shrinking, which is 0.60 to 0.72. If you ask even more, it will shrink even more, and you'll get better and better estimates. Okay, there is a direct formula to do it. And just to show that there is a formula, I have shown you, if you put the formula, this is what the curve you will get. Okay, and the underlying samples will always fall in this. So this is like your Galton board example that I showed you earlier, right? So there is a formula to do that. Okay, so anyway, I wanted to talk a few more things, but I'm out of time. So let's just stop here. So I will just say a few words about this article that I said I promised that I will do, but because of lack of time, we will not be able to reach that. So this appeared day before yesterday, and I have taken a printout of it. Okay, so all I am saying is that see, it says that it doesn't offer protection. Okay, so there is it offers protection. So I'm trying to say that it is not, I'm not saying the article is wrong. Statistically, there is nothing wrong here, but the newspaper article is trying to project in a way that is scaring us. Okay, so this is exclusively for Delta variant. Okay, so the point is they don't have enough data to conclude that it offers protection. So there is the window, the confidence interval is very wide. As a result, they are saying we cannot offer, it doesn't offer protection, but actually it does. Okay, so I think it does. So we need to have more data samples to verify this. So it's not as bad. So that's essentially what I wanted to say. I mean, if I had time, I would have actually gone through the entire paper with you, but I think it takes too much time. Any case, so let me just quickly recap. So what we did was we went through various machine learning concepts, and we saw that many of them are actually some things that people have looked historically as well. And conditional probability, conditional expectation are the two pillars of supervised learning, right? And we saw one example of Bayes' rule, and we saw some motivation of central limit theorem. Okay, so yeah, so that's all I wanted to say. And again, thanks to the organizers for giving me the chance to speak to all of you. If there are any questions that you would like to ask in the topics that we have covered, please go ahead.
Yeah, thank you, Satya. So any questions from the audience?
You can either type in the chat window or you can unmute yourself and ask.
Yeah, you have a choice there.
Good evening, everyone.
Yeah.
Yes, sir. For prediction of whether a patient is COVID positive based on the test report, can we just allow ourselves to stick to the confusion matrix and get the sensitivity and specificity of whether the patient is actually positive or negative?
So confusion matrix is basically sensitivity and specificity, right? So
yes.
So it is coming. These are the numbers. I mean, this is actually the numbers that I got from internet. I mean, I may be wrong, but this is what I got in several places. So it is a fact that 67 out of 100 people only will test positive, and 99 out of 100 healthy people will test negative. So these are the facts. Okay, so what is the question we are asking? So you don't look at the person's at all. You just look at the report. You just catch somebody at random, you do the test, you look at the report. Okay, Okay, and I'm asking whether he has positive or not. If you want to say, all we can say, if these numbers are true, is that this is the chance that he actually has COVID. Okay. So if you want to make it more concrete, you have to see at other features, right? So this 0.26 is probability that he has COVID, okay, given positive RT-PCR, right? But you can add other things. You can ask what is the probability that he has COVID given positive RT-PCR and fever and breathing difficulties. And when you put all of that together, then the number will be much higher. Okay.
Yes, sir. So the true positive and true negative value should be as much as high to get the accurate decision.
Yes. So if you have to have this, I mean, if at all this has to be meaningful, this has to be close to 1, and this has to be close to. So this, okay, specificity. I have written the wrong formula. Specificity is like positive. I think it is positive. Anyway, it is just 1 minus this. But any case, this number has to be close to 1, and this also has to be close to 1. So then you will be fine.
There is one question in the chat box from Jovi. You can see, do features have to be normally distributed?
No, not necessary. Because see, for example, normal distribution has support minus infinity to plus infinity, right? So normal distribution, if you look at it, let me draw somewhere there is space. So it has this support. It goes.
No, you are not sharing the screen right now.
Oh, really? Okay. Oh, I was sharing something else. Okay. Anyway, so normal distribution has this infinite support. Okay, but some features that we measure, like for example, height and weight, even though they look like normal, almost always they look like normal, but they are not. You cannot have negative heights, right? Negative weights. So yeah, it is not necessary at all that the features have to be normally supported. Yeah, it need not be. But central limit theorem is saying that if several unrelated things are adding up, they might look like normal. Okay, so there are many other patterns. This is normal is one pattern. There is Poisson pattern. There is other patterns that will occur in nature. So you have to use appropriate patterns if you want to go via the probabilistic route. Okay.
Yeah. Any other question from the audience? Yeah, so if there are no questions, let's thank Satya for this wonderful talk. Satya, it is nice to see, you give a talk on a public platform. We hear a lot from our students that you are one of the best teachers. So I think we need to give the test of your, teaching to the wider audience in Goa. Satya just joined 2 semesters back, and he has been teaching probability and statistics course at IIT Goa. It's a large class, and he's one of our popular teachers. So it's nice of you, and I am very happy to see your whiteboarding skills, because we when we switch to PowerPoint, we lose these writing on the board skills, and the pandemic has now brought us back to the whiteboard, because we can't explain unless you write something on the board which is shared.
Yes.
Yeah, so
thank you so much for your kind words. Thank you for inviting me. I think it was good fun to speak to you all.
Yeah.